Okay, hello, how you doing? I'm Peter Bandettini, and uh, this is this is the third year that we're recording these lectures and putting them online. So in case so there's a couple of announcements. First of all, well, welcome to the course, and it's an informal fMRI neuroimaging course. This year we've expanded it out to more neuroimaging. As you can see from the schedule, it starts out with a little bit more MRI, some general history stuff and general stuff about fMRI, and it kind of goes into some specific types of analysis methods. And then one thing that we did differently this year is we thought we'd include other imaging modalities. So having MEG, we have PET, we have now also we have things like neuromodulation as well. So we have another number of other people at the NIH who are doing these sort of things, and so figured it would be useful to have them talk about them as well. And the level is sort of pitched at everyone from summer students to PIs. So I think that there'll be something that anyone can get out of for the whole course. And one other announcement is that the way we've been announcing the courses in the past has been just either on fMRI Discuss or 3T Announce. But I think we'll start, after about 2 or 3 weeks, we'll move to a specific mail list called fMRI Course. And I think most of you should have the email or the instructions on how to go on to that mail list. So we don't bother or just add spam to the other email list then. So, okay, all right. Other than that, there'll be 3 lectures a week. This is kind of a unique situation. I had to, on short notice, go out of town the rest of this week. So I have to get just 2 lectures back to back. It will probably be 1 lecture going a little bit long, and then the next lecture will go a little bit shorter. So, okay. So what I'm talking about today, is I'm basically having the first lecture, and that is a very brief history of neuroimaging and a little bit longer history of fMRI. So neuroimaging, I figured I'll just round it out since the course itself is on more general to neuroimaging. This history is not really meant to do anything but just build perspective. The details of the imaging methods are for elsewhere when people talk about them, but I'm just sort of giving a general history overall. Okay, so this is my outline. So the idea is that I will talk about 4 different types of techniques. I won't do any of them any decent amount of credit or service, but I'll spend, like I said, a lot more time at fMRI. And to begin, starting with lesion-based mapping, and then going into just general anatomic imaging, hemodynamic and metabolic imaging, electrophysiologic imaging, and functional MRI. And so probably the oldest technique for mapping, if that's what you want to call it, mapping the brain, is finding out the areas that are damaged and seeing what happens to the person or animal and seeing how they don't work. And that's obviously, it's still going on. It's still taken to a very high level. But some of the first most notable results have been, probably the most famous result has been in 1861, Paul Broca. He had a patient, Liboren, who could only pronounce the word tan, and he found that this corresponded to this massive lesion in their brain. So this part of the area of the brain was then inferred to be the area that is involved with elucidating or saying words clearly, or having a wide repertoire of words. So then, similarly, Carl Wernicke in 1874, about 13 years later, he had a number of patients who could not understand or produce meaningful speech, but could actually produce words. And this was a very different area of the brain that was damaged. And this was an area a little bit more anterior, and hence it was called Wernicke's area then. That areas correspond to that. And these areas are both on the left side of the brain. They correspond to, of course, language production. And each one, was the first thought that the brain is actually modular, that is actually divided into modules that have very specific purposes. And if you damage these modules, you don't damage all aspects of the function, but only certain specific ones. So that was sort of the beginning or the prehistory, some of the prehistory of neuroimaging. And so hence these two aphasias have become very well known. There's Broca's aphasia and there's Wernicke's aphasia. So Broca's aphasia basically is essentially difficulty with articulation, whereas Wernicke's aphasia is disruption in both recognition of spoken words and comprehension of the meanings of words, and also putting words into coherent thoughts. They say a lot of words, but it doesn't really make a lot of sense. Okay, so that was the quick history of lesion-based mapping. Very, very brief. Anatomic imaging. All right, so I like to trace anatomic imaging back to Röntgen, who in 1895 discovered X-rays and their utility. So essentially, back then, people were playing around a lot with these sort of tubes that were basically almost light bulbs, but there was, instead of having a filament, they basically had a cathode and an anode, and they were a vacuum tube. And it turns out that if you pass enough current through this, it turns out that the electrons, when they run into certain specific types of metal, they emit X-rays. And it could either be tungsten or copper. And they just discovered this by accident, that he wrapped a film around this. He wrapped like film paper around this, and he found that it was exposed. And that was sort of curious. And so basically, he did a few more experiments and put his hand in front of it and realized that he was able to image hard tissue. That's where the X-rays did not pass through, basically the bones in his hand. So that was a serendipitous discovery. So, and that obviously led to all kinds of other things. So there's techniques that have evolved from X-rays. So in the early 1900s, people did a pretty amazingly invasive thing to get a little bit more contrast in the brain. They drained, they've done this from time to time, they drained the CSF from the brain to enhance the contrast in X-rays. So CSF, because it has the same density as the brain, essentially, if you drain that out, you get more of the edges. And so that was a kind of barbaric way to sort of enhance contrast, but I can understand the desire to want more contrast. Okay, and this was the first, in 1927, the first arteriogram. Antonio Igas Moniz. He also, I think, was the same person who invented the lobotomy as well. So all these people were really into brains, and he basically injected a contrast agent that blocked X-rays, and so it allowed a little bit of contrast with the vessels. So this is one of the first angiograms ever created using X-rays. And then you go till, from 1927 to 1960 with William Oldendorf. He figured out how to make specific slices. And then quickly from there, you have relatively quickly, another 9 years, you have the development and the implementation of the CT scanner, which was essentially a three-dimensional sort of X-ray that sort of went around and scanned the body, took back projections, and then recreated the image in 3 dimensions. So that was the first CT scanner implemented by Hounsfield, 1971. All right, so then you have MRI, which came about shortly afterwards. And these people are the two that are credited with sort of, there was a big history of MRI that I'm not going to go into. It's involving NMR and the development of NMR. But these people were basically the ones who turned it into a clinical technique because you could do imaging with it. So this is Sir Peter Mansfield, and Paul Lauterbur. They won the Nobel Prize in 2003 for doing this. And essentially, Lauterbur's contribution, this is just taken right out of a webpage, but it really nicely summarizes things. Now, Lauterbur's contribution was something called zoomatography. He named it that, in which if you have a rotating gradient, it was a very crude, but it worked, way of doing spatial encoding of images, going from a spectrum to spatial encoding using magnetic field gradients. And I'm not going to go into too much detail with this, but his paper was published in Nature in 1973, and turns out it was rejected multiple times and finally was published. He had a good quote of, you you can actually look at the entire history of science by all the rejected Nature papers. So Mansfield's contribution was a little bit more involved. He actually came up with the concept of slice selection using a gradient. And actually, so this was actually using rotating gradients in which you found projections, and reconstructed the image, which we don't use anymore, except for it was sort of like a CT method of doing imaging. Whereas Mansfield had a totally different sort of take at it, where he actually used gradients magnetic field gradients. So basically protons precess at frequencies at which proportional to the magnetic field gradient. And it turns out that if you apply a gradient across these resonating protons, or any other NMR sensitive atom, you can actually see they basically precess at different frequencies. And if you just look at the spectrum, it's a mixture of frequencies. And then if you take the Fourier transform of the spectrum, you can create the spatial location of wherever that was coming from. So he did this, and he basically scanned through, and it was able to create a picture of a human finger and other things. He also actually, Mansfield is credited with actually coming up with the concept of echoplanar imaging. So one of his first ideas, he didn't develop K-space, which is a different sort of formalism for looking at imaging, but echoplanar imaging is where you basically raster through raw data space very quickly and then create an image from there. And the idea is that it's conceptually easier to understand than multi-shot imaging. And he laid this out before it was even really possible to do this. You didn't have gradients that could switch that fast. And that was back in 1977. Okay, so this other guy, Damadian, also claims that he was gypped when they gave out the Nobel Prizes. And he has potentially an argument, although he didn't really do the imaging part. He had basically his method. So he did two things for the field. One, he sort of helped catalyze it because he showed that different types of cancer changed the T1 relaxation. It was preliminary data, but it seemed to work. And two, his imaging method was really bad. Instead of actually using some trick with gradients or back projection, he actually just he had one sensitive point where you image, and he basically had to move the person around to actually make the image. And it took like an incredibly long time. He called it field-focused NMR. And this was an image which looks really good. It just took forever to create. And for that and other reasons, he was actually left off the Nobel Prize list, which is still somewhat controversial. But most people in the field sort of agree that Mansfield and Lauterbur were part of the mainstream of the science going forward. He was doing something off on the fringes. Nobody really understood exactly what he was doing. Kind of worked, but it never really caught on in the future. Okay, other ways of looking at brain function. So hemodynamic and metabolic imaging. So this is a classic experiment that there's actually just recently a book came out about Angelo Masso in 1880s, in which basically he had a person lying on a table. It wasn't an imaging experiment per se, but essentially you had a person lying at a table, and they were balanced very, very, very carefully. So basically, if you had a redistribution of the blood, the table would tip one way or the other. So what he did was he had this person, he basically gave them either sound or certain thoughts sort of experiments, and he found that if he did this, the table would tip towards his head. So the idea there was that he was looking at a greater blood volume that would rush into the person's head, and that's the way he actually assessed that the brain was active, because the blood volume increased, and this was the first way of looking at it. It's a little bit controversial whether it actually worked, but it's an interesting story. So that was back in the 1880s. So 60s and 70s. So essentially, there's a whole culture in Northern Europe of doing tracer kinetic studies. And Before there was imaging, there was the Ketty-Schmidt equation that basically was able to assess blood volume, infer blood volume by looking at the difference of tracer accumulation between arterial and venous blood rushing in and out of the brain. This was the first imaging experiments, and actually it kind of dates me. I remember looking at, in some sense in high school, at Scientific American articles that looked something like this. This is essentially, you have radioactive tracers that are either inhaled or injected. This happened to be xenon, and you basically had scintillation counters around the head trying to infer where the radioactivity was depositing itself. And these were some of the first images. And credit should go to Neil Lawson, David Ingvarg in particular for that. And that was in 1978. Okay, and then PET came along, and this very quickly, PET is a little bit different than that in the sense that you can localize the source a little bit better by what's called coincidence detection. So you have these various isotopes that if they're emitting radioactivity, if they run into tissue or are stopped, they emit gamma rays that go in two opposite directions. And so from the simultaneous opposite direction, you have essentially detectors that detect the coincidence of where these are occurring to then infer where they originated. So that's the basic concept of PET. It will be explained much better in the later lectures, but I'm just sort of going over the basic concept. Various people had developed PET scanning. In 1973, Michael Terbourgosian, Edward Hoffman, Michael Phelps actually created the first human PET scanner. This was in 1973. Then in 75, you can see the progression from 75 to 95 of the image quality and sensitivity. And now PET is pretty high resolution. It's still getting better, actually, as we get closer detectors, better detectors, more sensitive detectors. And now we have simultaneous PET and MRI as well. Okay, and these are some of the classic pictures that also sort of inspired me in high school. Actually, this was in college, but this was from, is this still on? Yeah. Okay, so these were some of the first brain activation studies. So notice I didn't talk at all about activation up until now. So this is the first studies in which you did, which they had subjects either hearing words, so you have auditory cortex activation, seeing words, visual cortex, generating words, and speaking words. Generating words this is Broca's area, and speaking words, you have the motor cortex. And this was published in Nature in 1988. So, and then by then, PET was sort of in its golden time of sort of producing, everyone who did brain mapping, brain function mapping was doing PET at the time. And that was just before fMRI came along. So PET was in its heyday right now in 88. Okay, so there's electrophysiologic mapping. And once again, without going into too much detail, it goes back as far as 1875, where Richard Catton measured currents between cortical surface of skull in dogs and monkeys, so it actually saw something. In 1924, Hans Berger measured EEG in humans, was the first to describe alpha waves and beta waves. And looking at extremely low voltages, 20 microvolts. And about 50 years later, in 1968, there was people were measuring magnetic brain signals, magnetic field fluctuations at the surface of the skull as opposed to electric fields. And 1970, there's a breakthrough in detection. People, basically the superconducting quantum interference device. Essentially, it's a superconducting wire that's placed over the head in which any current, any magnetic field that's produced in the head induces a current in that wire. And because it's superconducting, it has zero resistance, and so it's super sensitive to any magnetic field on the surface of the head. So that was 1970. By 1972, you had a one-sensor MEG, and now you have, this is an EEG, multi-sensor EEG. You have up to 500 sensors MEG, I think. So we have, the technology has advanced considerably, But because, unfortunately, especially with MEG, is a little bit disappointing because it can go probably a lot better. It can get better, but it hasn't yet found a clinical application that it can find traction with. So it hasn't really been driven by the clinical market as much as for instance, MRI. So it's still at this stage where it works really well. Things are advancing, but not quite as fast as MRI. Okay, so now the whole rest of my lecture is devoted to functional MRI. All right, so what I like to usually start out this lecture with is a Neuroimage special issue that came out in 2012. And it was pretty much a summary of over 100 researchers' personal experience of pushing the field. These are researchers who have done mostly methods development, everything from the hardware to the sort of bridging the gap between the methods and applications. And without going into too much detail, you might recognize some faces here. Rainer Goebel, there's, all kinds of people that are many here at the NIH. There's Dan Hanwicker, there's Steve Smith, who's at Oxford, and so on. So these are the names in case you're interested. You can download these slides within a couple of days from now. And these are the topics covered. So what I like to just show here, I'm not just portraying the special issue, but this is sort of how method development in fMRI has evolved over time. You have pre-fMRI, which is essentially PET or neurovascular coupling and issues like that. The first fMRI brain activation results, development of pulse sequences, methods, and integration with hardware, that's still evolving. The emergence of processing and display packages, the development of processing methods, other methodological developments. We're always coming up with new ways of extracting information from the fMRI time series. And so this is sort of a snapshot of when that occurred. New paradigm designs, and also education, and then the future. So, okay. So here's basically a snapshot of the field of functional MRI. This was a Science article. It was a review article in Science published by authors here at the NIH that were at the NIH at the time: Krit Moonen, Peter Bandettini, Joe Frank, who's still here, Denis Lebihan, and Edward Becker. And if you look at this was in 1990. What's missing is what we call functional MRI today. And this actually came along about a year later. But you did have things like angiography, was able to look at blood flow. You had gadolinium perfusion, able to look at blood perfusion and how it traversed through the brain. You had diffusion imaging, which was in its early days. Actually, Peter Basser, who's here at the NIH, developed an aspect of diffusion imaging called diffusion tensor imaging. Denis Lebihan was actually also working on diffusion imaging at the time. Magnetization transfer, Bob Balaban conceptualized that advancement. Bob Balaban's here at the NIH. Essentially, that looks at macromolecules and basically how much free water is around macromolecules. It's the environment around the tissue. It's novel relative to like T1 or T2. You have metabolic imaging. Basically, it's spectroscopy, but spatially encoded spectroscopy, where you can actually look at various metabolites as well. So this was the state of the art in the 90s, in the early 90s. And suddenly fMRI came along. So what I'm going to outline is the key factors that were involved with fMRI coming along. Okay, so you had to have some unique properties of the red blood cells. You had to have something unique in the brain that happened with activation. You had to have a certain spatial scale so you could see it. And you had to have high-speed, high-stability imaging. And you had to have a lot of MRI scanners for the field to really take off. And I'm going to go into each one of them. So as far back as 1936, or even before then, Linus Pauling knew about the fact that blood, when it became oxygenated, it had a similar susceptibility as the rest of tissue. When it was deoxygenated, it was it was paramagnetic. It basically concentrated magnetic fields relative to the rest of tissue. In 1982, Keith Tholborn discovered that it turns out that this susceptibility effect actually changed the relaxation properties of water, mostly T2. He didn't measure T2 star. He measured the T2, which is the transverse relaxation. It changed that. And he figured, okay, that's very interesting. It might be useful. In 1990, Ogawa actually coined the term BOLD contrast, blood oxygen level dependent contrast, and was the first to demonstrate in vivo that you could actually see oxygenation changes in the blood. And then Bob Turner essentially did it also in cats as well. So by the way, I mean, once again, people taking notes or whatever, you can download these slides from our website. So don't have to worry about just taking notes or doing anything like that. So, okay. So then, so this is basically just quickly going over that again. So this is a paper, this was Linus Pauling's paper where he actually describes the susceptibility effects. And he sort of criticizes Michael Faraday, saying that, oh, well, if he would have just had blood as opposed to dried blood, if he had it actually in suspension, he would have discovered this way earlier than myself. But he didn't. So, and this is Keith Filborn, who was a spectroscopist who worked with George Rada in the UK. And this was his experiment. And essentially, he basically changed the oxygenation of the blood and just looked at its relaxation. And it had this beautiful correspondence to oxygenation. And I'll get into more of the details about this in a second. One thing he did also show, and this is a little bit more of an esoteric side, and that is that if you have a change in T2, it could be for a number of reasons. It could be direct what's called dipole-dipole interaction. It's more of a microscopic sort of interaction that may or may not be due to bulk susceptibility effects. So he essentially modulated his pulse sequence such that he proved, using a pulse sequence modulation, that it had to be that it was the magnetic fields around the red blood cell that was changing the T2, as opposed to water molecules directly interacting with the molecules in the red blood cell. That was not the mechanism. So he proved this using this pulse sequence, which I'm not going to go into, but it was essentially, it was a very important thing to prove as far as that's concerned. And then Seiji Ogawa came along. He was studying blood for most of his career, and he decided to actually try MRI to look a little bit more carefully at it. He was using ESR before, and he was the first person to actually, as I mentioned, put a mouse in the magnet, and this is what he showed. So this is at 7T in an animal scanner, and he showed that if you gave the mouse 100% oxygen, if you completely saturated the blood with oxygen, you had almost no contrast with a T2 weighted sequence, or actually here he had a T2 star weighted sequence, and which is a gradient echo sequence. If you gave the mouse, if you reduce that to 20% oxygen, which is typical of room air, you have, because there's a metabolic rate in the brain, pulling the oxygen from the blood, then you have a little bit more deoxygenated blood on the venous side. And so you can see the veins popping out as becoming darker as they become more paramagnetic relative to tissue as they become deoxygenated. And he also showed this in a test tube as well, that with 100% oxygenated blood, you have something that just looks like a dark dot. With 0% oxygenated blood, there's this massive penumbra that kind of shows up around it. And he really liked the fact that there was a penumbra effect, because that was sort of an amplifying effect of the blood effect. So people would argue that, oh, there's only 5% blood in the brain. How can you even see this effect? Well, the fact is you're not only looking at the effect of inside the vessels, but there's spillover, the magnetic fields around the vessels that are causing this dephasing of the signal. Okay, this is what it looks like. So this is essentially what happens. So if you have a blood vessel right here, and this happens to be slightly deoxygenated, you have a paramagnetic substance right here, and this happens to be perpendicular to the magnetic field. It's somewhat of a function of angle, but it still shows up as distortions around the vessel, regardless of the angle, except with few exceptions. And you have magnetic fields set up that essentially, if you have a spin or a proton experiencing this magnetic field, this will be processing faster than the spin, a few hundred microns away, experiencing this magnetic field. And so these spins that are still within an imaging voxel, they get out of phase really quickly. And so when they get out of phase, they destructively add and the signal goes down. And so that's why if you have distortions around these magnetic field perturbers, which would be deoxygenated blood. That's why the signal it goes down, because it's dephased. Okay, and then Bob Turner and Denis Lebihan here at the NIH did an experiment where they shut off the oxygen to cats. So here's a time series of images where here is the cat breathing normal room air, and then they induced apnea at this moment right here. This is the image they used as the subtraction image, where all the subsequent and previous images are subtracted from that image, or that image is subtracted from them. I'm sorry, the other images are subtracted from that one. And you can see actually the signal very quickly getting darker and darker and darker and darker as the brain becomes deoxygenated, as the cat is still alive, and of course its metabolism is going, and it becomes deoxygenated right here. You can see the signal right here from the cat brain. And then suddenly when the oxygenation is reintroduced, there's a reactive hyperemia a little bit, and it goes back to normal. So this was actually a very exciting. This is also pre-fMRI. So everyone here is like, okay, this is really a sensitive contrast agent. Now, maybe it could be used for people. And it turns out that Ogawa, in one of his papers talking about this, predicted that fMRI would work. He just got the sign wrong. So this is a quote from his magnetic resonance in medicine paper saying, we expect the oxygenation-sensitive contrast to be modulated when your brain becomes active. And he assumed that the more active region would be pulling oxygen from the blood, and the signal would go down. He didn't know the PET literature, and none of the physicists really knew the PET literature that just was starting to come out with information that, in fact, the opposite happens. There's an overabundance of blood that rushes into the brain, and the oxidation actually goes up. And so basically, though, he had it right, though. In addition to the anatomy of the brain, one aspect of its physiology can be studied by MRI of water, and that was brain function. So, and that goes on to my next part of the talk, and that is the first functional MRI results. So the first results were not using bold contrast. The first results were actually using gadolinium contrast agent, which is also a paramagnetic substance, much stronger. It has much stronger paramagnetic properties than deoxygenated blood. It's still used today. It's used every day clinically to map out brain perfusion. And essentially, this is what the experiment was. This is Jack Belleville did this. He injected a contrast agent. This is a time series of echoplanar images. MGH was unique in the sense that it was one of the only centers that actually had echoplanar imaging running. It was using a retrofitted sort of resonant gradient system because it basically drives the gradients extremely hard. And you essentially inject the tracer right here. It goes, once it gets in the brain, it causes this massive signal decrease because it's paramagnetic, and then comes back out, washes out. And integrating under this curve on a voxel-wise basis, he was able to make a nice map of resting state blood volume. And then he shined lights into the subject's eyes and did it again, did this experiment once again, integrated under the curve and subtracted these two and came up with a map like this, which showed for the first time visual cortex activation. And this was published in Science in November of 1991. And as soon as this paper came out, actually, the technique was obsolete as far as a functional imaging technique was concerned, because Bold had come along from even a colleague in his own group, Ken Kwong. So it was a great, motivating sort of image. I remember I was just starting graduate school at the time, and this was extremely exciting to see. This is the group that sort of pioneered that. There's Jack Belleville right here. Bruce Rosen was his boss, or actually Tom Brady was his boss, but Bruce was one of the bosses. You might recognize some of these people. Ken Kwong was the person who had the first fMRI experiment. Van Wedeen has been pioneering since flow imaging, and now he's doing diffusion tensor imaging. Okay, there's Jack right there. So Jack actually passed away just a few years ago, unfortunately. So, but his legacy lives on. So this was actually the precursor to bold contrast, and that is that this is a PET experiment. Was the first time that suggested that this was by Peter Fox and Mark Rakel. And here they had a subject. They were stimulating a subject's somatosensory cortex with a vibrating ball in their hand. And they found actually that with PET, they were able to measure the flow increase, and they were also able to measure the oxygen extraction fraction. And what they found, well, actually, they were able to measure the flow and the CMRO2 and induce what the oxygen extraction fraction was. And what they found is that there was a decrease in oxygen extraction fraction, minus 20% from the mean, in the active areas. And what that meant is that even though the metabolic rate went up, the flow, the delivery of blood to that area went up even higher. So the relative fraction of oxygen that was extracted went down. So there's an overabundance of oxygen in that area all of a sudden. The rate of oxygen extraction actually went up a little bit, but still the fraction of oxygen went down. So here is before I get into bold contrast, I'm just going to lay out the flow chart of what happens and what's interesting about what happens. So you have cerebral tissue activation causing a local vasodilatation, which we don't completely understand all the mechanisms for this. We understand what all the possible mechanisms could be. We don't really know exactly what the mechanisms are, though. It could be neurogenic or some sort of chemical mechanism. You have an increase in cerebral blood flow and metabolism, or blood flow and volume, that leads to an overabundance of oxygen delivery to metabolic need. This is also somewhat of a mystery. We don't know why there's this overabundance. It could be that to get oxygen to the furthest active cell away, because there's an exponential drop-off of diffusion of oxygen to that furthest cell, you might need this overabundance in the blood. That's one model. And that works for me, actually. That seems to make sense, but there's other models as well. And you have an increase in capillary and venous blood oxygenation. So this leads to, or is related to, a decrease in deoxyhemoglobin. And that's the key. And so it just happened to be a fortunate thing in nature that hemoglobin, as I mentioned, is paramagnetic when it's deoxygenated. It's diamagnetic like the rest of tissue when it's oxygenated. So it's invisible when it's oxygenated. It becomes a dark dot when it's deoxygenated, or dark. And so with activation, you have a decrease then in susceptibility-related intervoxel dephasing that increases T2 and T2 star, which are quantitative measures of relaxation rate. And then the local signal increase in these two sequences increases. Okay, all right, so the first experiment, this is Ken Kwong, 1992. He had his PNAS paper was published in which he was looking at both perfusion changes. He actually had a novel method for looking at perfusion, and also a novel method for looking at signal intensity with oxygenation. He didn't call it bold. I don't think that anyone called it bold until, I don't know, maybe a couple papers later. Or maybe he did say bold. I'm not sure exactly. But either way, they knew it was oxygenation, though. So, and essentially you have this is the first time series. And they actually did a nice experiment where they compared it with PET with various flicker frequencies, and they found that it sort of compared with metabolic rate, or PET CBF measured. And here are the maps right here. So here's his notebook, which is actually, Bruce Rosen shared this with me. One thing is that it's May 9th, 1991, which is just a few weeks ago, 25 years ago. So it's almost exactly a quarter century ago that this happened. And if you also look at his notebook, he likes to highlight that Ken had made the original block design paradigm right there. And he was using bold contrast right here. And he also was using CBF contrast right here with these are the parameters right here. And his bold contrast was 40 milliseconds. He knew to actually have a longer TE with his gradient echo. A lot of things were quite insightful at the time. Other groups, though, were working on this as well. So there was, Ogawa was collaborating with the University of Minnesota. Ogawa was in Bell Labs, University of Minnesota was waiting. They actually waited. Their claim is that they would have done this a lot earlier, but they were waiting for their high field magnet to be installed and to work. And so even though they could have done it at 1.5 Tesla, so for instance, these results right here were at 1.5 Tesla. They waited till 4 Tesla, and they got beautiful results. They were using not echoplanar imaging, but a multi-shot technique, which is a little bit noisier. And they actually found that they did another experiment that actually helped to show that it was a T2 star contrast. They varied the echo time. They had a short echo time, 8 milliseconds, and a longer echo time, 40 milliseconds. And they found that quite clearly the amplitude of the effect increased with echo time, which helped to demonstrate that it wasn't motion, it wasn't T1, it wasn't proton density, it was actually T2 star, which actually increases with echo time. So that was a nice experiment that confirmed that, and beautiful results. So as I mentioned, that was a multi-shot technique. Most of the people doing fMRI even today use single-shot techniques, and you essentially have, this is just a quick, I just want to very quickly illustrate to you what echoplanar imaging is. Essentially you have, you give an excitation, a 90-degree excitation pulse, and then you have your encoding gradients, which have to do the spatial encoding. And you apply all these gradients at once. There's no waiting and giving another RF excitation. But when you do it all at once, you have to raster the gradients extremely rapidly to spatially encode. And while you're encoding, there's T2 star decay. So by the time you're at about 50 milliseconds, the signal's gone. So that's why the echoplanar images generally are lower resolution, because you just run out of signal. If T2 star were 200 milliseconds, we'd have beautiful echoplanar images. We could just collect for that much longer, but unfortunately it's not. So we're up against that physical limit. So for fast imaging, like I mentioned, MGH had a special retrofitted resonant gradient system. The Minnesota group had standard gradients, but they used multi-shot, and they used a trick called navigator echoes to actually fix the NMR phase, because it was very sensitive to respiration and cardiac. They actually did a good job fixing it, so the images were stable. And there's another group. This is the group I was at, Medical College of Wisconsin. We actually used a local head grading coil that was built by Eric Wong. Here's Eric Wong. Here's his design. He basically used a method that basically moved the wires until it optimized for a linear gradient field. And this is us way back in August of '91. In the machine shop, milling away, making this thing out of broken, there's like a little chip broken off of there. It's like sewer pipe and wire and epoxy, sticking it onto a scanner to get it working. And this is a couple versions of ours. We had this local grading coil right here, and this 1991, 92 version, 92 to 99 version right here. And our first experiment was basically, we could only collect one slice, so we collect a big, massive slice through the motor cortex. And one little known fact, though, and this is always in retrospect, it's always interesting to think about these things. We actually didn't need a grading coil at all. And none of these groups actually could have really needed a grading coil. You could have collected perfectly good data at 5 millimeter cubed without the grading coil. You could do that on your standard 100 amp, low, really wimpy gradient amplifiers that they had at the time. Everyone could have been doing echoplanar imaging with their standard coils, collecting sort of low resolution, but still functional data, functional MRI, single shot echoplanar imaging. So, but we had the grading coil, we built it, we did it, and these are some of our first results. We came out in '92 as well, a little bit afterwards. This is one of the first movies that we made of left and right finger tapping here. This is an axial slice. Okay. And this was my notebook. It was kind of funny. This is actually, the funny part is that I was looking for signal decreases, because in Ken Kwong's movie that he showed, and also based on Ogawa's paper, I never really knew the sign of what should be happening. And the signals I saw kept on going up, and I was expecting them to go down. And so I was sort of confused by that. I had to go back to the literature and figure that out. So we did our experiment in September 16th, 1991. So. All right, so that's a little bit of that history. And then what are some of the things that sort of have been developed along the lines? So there's, so this is essentially, this was the fourth paper. This came out of Yale. This was Andrew Blamire and Schulman, among other people. They did the first event-related fMRI. They didn't call it event-related, but they would shine light for 3 seconds into people's eyes, and they elicited a really nice response. And so this was published in PNAS in 1992 as well. And during this time, there was another technique that was coming out for looking at baseline perfusion imaging, and also perfusion changes with activation. This was being pioneered by Alan Koretsky's group. So Alan Koretsky's here at the NIH, and so he was simultaneously working on that. He was actually on to BOLD, but he was more focused on getting quantitative metabolic measures. And so he sort of like went right beyond BOLD and kept on working on trying to get his quantitative metabolic measures and sort of missed the BOLD bandwagon, so to speak. At least that's the way he says the story, which I believe. But so basically they were the first to develop arterial spin labeling. So that method is where you essentially apply an RF pulse to tag inflowing blood. And you allow the blood then to flow into the plane that you're interested in, and then you image, and then you do another image where you have a control tag with no blood, and you subtract these pairs of images to get a map of perfusion. And so these were some of the early perfusion maps, and this as well, that came out. Also in about 1992, or 91, actually. So, and this is the basic concept, as I just mentioned. You suddenly had a huge slew of various versions of arterial spin labeling. There's something called Epistar. Actually, this was developed by Bob Edelman, in which you would you would have to actually tag, image, tag, and then subtract. FAIR, which stands for flow alternating inversion recovery, which you basically tag everywhere and then image, and then don't tag everywhere, and then you get bidirectional flow contrast. So, and this is the concept of perfusion shown right here, where if you give a tag, if you only wait 200 milliseconds after you give the tag, it looks like angiography. So this essentially is time of flight angiography if you only wait a short amount of time and you get only the large, most rapidly flowing vessels. But what this technique allowed you to do is wait a little bit longer. So you could wait up to a second. If you waited up to 1,200 seconds, basically had the magnetization affect the magnetization in the tissue, and you have these nice maps of gray-white matter contrast that corresponds to perfusion. Okay. And these are some of the first, these were the first BOLD papers that came out. This is, as I mentioned, Blamire, then Fromm also had a high-resolution one, and we went from there. So there was a lot of sort of interesting jostling about of names and things like that in the early days as well. So Bob Turner, this is a meeting that was really a cool meeting back in June of 1993 that occurred right here in DC. And what's kind of funny is that Bob Turner was really pushing hard to call fMRI MRFN. And it didn't really catch on, but it's almost too bad, because then the way you look at that, it sounds like more fun. So fMRI is more fun than the regular MRI, which is true, which is actually true, at least my view. Anyway, so that was Bob's take on this, and this is Bob's paper. It came out about a year later, about a year later, which here at the NIH, they finally got their 4 Tesla and 1.5 Tesla working. They did the first field strength comparison showing that at 4 Tesla, the signal is much higher than at 1.5 Tesla. And this was with Peter Gizzard, and Ken also collaborated. And there's basically, they had a local gradient coil as well, just a Z-axis local gradient coil. And this is actually how far things have come. There's Peter, and then you have this massive 4 Tesla scanner that existed in Building 10 that they quenched about the year 2000. And now you have Siemens 7 Tesla scanners or even GE 7 Tesla scanners that have the same footprint almost as a 1.5 Tesla scanner back then. So they're getting a lot smaller and more efficient. They're not getting cheaper, though. That's for sure. So this 7 Tesla is now being sold for close to 10 million. So it's a lot of money. Anyway, okay. So what else had to be in place? Not only did we have to have just the right susceptibility effects with red blood cells and just the right types of hemodynamic coupling. So one thing I want to emphasize, I mean, it could have happened that blood oxidation exactly matched metabolic need. It probably is a good reason why it hasn't happened, but let's say that happened. We would never see BOLD. BOLD depends on the fact that there's this uncoupling. And there was actually, in the early days of fMRI, there was this huge debate whether whether it was an uncoupling or whether it was a nonlinear coupling. People would debate this back and forth, whether things became uncoupled or were nonlinear. And now everyone realizes, well, it almost doesn't matter. It seems pretty consistent. It's a form of coupling that is fortuitous for bold. So another thing that's fortuitous for us, though, is that the brain is organized in this wonderfully coarse and modular fashion. So not only coarse, it's organized across several spatial scales that go way below what fMRI can see. But we're lucky, though, that on the one scale, the biggest scale, the system scale, there's big chunks of brain that do certain things, like visual cortex, the whole back of the brain lights up. Motor cortex, the whole motor strip lights up. This was very, very useful, and it's still useful today, sort of to do basic mapping of systems level functional MRI, because our resolution hits that sweet spot of these systems. Okay, so here's an example of motor cortex activation, but at the same time, you can get to very higher resolutions. So here's basically, as I was mentioning, the brain is not only organized across systems level, sort of macro scale, but it's organized across layers. It's organized across columns. And both these columns and layers have very unique functional information that we're just starting to tap into with fMRI. So here's some early results, really nice results. Both of them were sort of like a tour de force, in which they were, so comparing to optical imaging, this is a technique I did not talk about that much. Essentially, it's looking at the reflectance of light with blood oxygenation, and showing essentially that, and also with blood volume, you can see both. And you can see that you can easily resolve columns if you expose the skull, and this actually happens to be in an animal brain, exposing the skull, shining infrared light, and looking at the reflectance changes with activation. And it turns out that if you shine light if you stimulate one eye versus the other eye, you get a columnar type of activation. And this is very finely detailed. So this is actually on the order of 1 millimeter column widths. And the first results that showed this columnar activation resolution with fMRI was by Ravi Menon in 1997 and Kang Cheng in 2001. And both of them show somewhat similar results. Kang even chose the same color scale, I guess. So, and here's results there. Essa Yaqub actually at Minnesota was able to take this one step further. In 2008, at 7 Tesla, they did an experiment looking at orientation columns, in which it turns out that the subject was looking at a stimulus that was a grating that was rotating. And it turns out, and first they did ocular dominance columns. They showed stimulus in one eye versus the other to map out the columns, and that's delineated by these lines right here. And the orientation columns are this continuous, and I'll show you more clearly illustrated with the movie, of these basically pinwheel type of organization. You can see the pinwheel pattern right here as basically as the stimulus rotates. If you spatially encode it by color, that's what they did, you can map out this pinwheel organization. So this was basically a black and white depiction of what became active as the stimulus was rotating. And here's another pinwheel pattern right here. So this result actually has never yet been replicated, but it's very believable here, and I certainly believe that they did it. It's just really hard. It's very, very hard to do. You have to do a ton of averaging. You have to have just the right contrast, and you have to have 7 Tesla. But at least it's doable. And what's nice about this is that this is what people believe is the limit of what the hemodynamic control, the spatial scale of hemodynamic control of functional areas are. So fMRI sort of is able to match what physiologically the smallest scale where we do hemodynamic, where we control the hemodynamics, the blood flow, which is on the order of columns. So this is actually some work I just put this in just recently. Also, there's nice work on layers that is just starting to come out, using a very different technique than BOLD, but BOLD still has potential for seeing this. This is Laurentius Huber, showing that the difference between this is sensory, and this is motor cortex, and actually being able to look at inputs to specific layers as they're modulated. So if you're tapping your fingers, you have motor cortex activation, but you also have a sensory input to your motor cortex to tell the motor cortex, oh, I'm tapping, I'm going to stop. It's proprioception, but also it affects the motor cortex. It's an input from sensory to motor across layers. If you just do this without tapping, that input is modulated. There's no longer that input. And he was actually able to see this with here's tapping with touch, tapping without touch. You have this lack of activation in layer 2 and 3 of the motor cortex. And you have an activation here. I'm sorry, this is, right, motor. And then, so you have basically this modulation of the input. So from S1. Okay, so that's actually, so it shows that fMRI is getting there. And so what's really important here is that not only is this super high resolution, and that's wonderful, but also we can start to ask questions of causality and connections with fMRI as opposed to just simply mapping areas, which is a nice direction. Okay, and there's no reason not to think that that the brain is actually organized in a columnar way across all types of other parts of the brain. So this is some work by Mike Beauchamp back when he was at the NIH of actually looking at, when you go to higher and higher resolution in your mapping function, you get less blob-like activity and more interdigitated, complicated patterns. And so this is an example of a task that involved visual, auditory, and multisensory integration. And instead of actually having these blobs of activation that are easily differentiable, you start to have this interdigitated, detailed activation that's very hard to make sense of. It's because you can't essentially just average it in 3 dimensions and average it across subjects and say, oh, there it is. It's hard to find a center of mass for it too, but basically it's the way the brain is organized at this lower scale that we're getting at. So essentially, this is a classic chart of where MRI sort of fits with all the other techniques. So you have MEG and EEG that are essentially very fast, but they are relatively coarse. Some people argue that you can get a lot higher spatial resolution with them, but I think you can, but your spatial certainty is still low because there's still the inverse problem. With PET, you can certainly get a large chunk of this area at systems level organization, but it's not quite as high resolution, both in space and time as MRI, and also it's invasive. And all the other techniques are basically techniques that you have to kill the animal to actually see the function. So fMRI came along at just the right time to sort of fill this large gap of systems level organization that we hadn't had filled before with PET and other techniques. Okay, so the fourth key factor that you needed for the emergence of functional MRI was a high-speed technique that was also extremely stable. So that was echoplanar imaging. So as I mentioned, with echoplanar imaging, you have, you're always fighting against this T2 star decay. So you give a 90-degree pulse and you raster back and forth as quickly as possible before the signal completely dies away. And essentially, what's important about echoplanar, though, and let me essentially, though, different from anatomic imaging, echoplanar imaging, most of the time you're collecting a time series of data, so you're comparing the contrast as evolves over time. And these are really old, really crummy images of echoplanar images that I should update. But just to illustrate the point that because you have a single shot, the image quality is not as good as you can get with multi-shot techniques, where you have a lot of time to spend to collect the data. Okay, and so here's, just to illustrate an important point, is that yes, there have been techniques that would have kept up with hemodynamic responses, multi-shot techniques in the early days. And yes, it was useful to have a technique that captured a snapshot and went very fast. But what's really important is the stability of echoplanar imaging. So with echoplanar imaging, you collect everything in about 30 milliseconds. Well, it could be much shorter than that now. It could be down to 10 milliseconds, but anywhere from 10 to 50 milliseconds. And with that, you freeze all physiologic motion, essentially. You freeze the heartbeat, breathing, so everything is captured. So what that means is that, so when you collect your data, you might have ghosts that might occur because of imperfections in how you collect your raw data space, but at least the ghosts are completely consistent over time because the relative location of each line of k-space is consistent. So if you have a heartbeat that occurs or breathing, that might change your position in k-space with a multi-shot technique. And here's an example of that. So if you have a technique that takes 10 seconds to, let's say, 1 minute to collect, you have lines of k-space that might be at slightly different locations because the phase or the relative location of k-space is affected by these physiologic processes. So you'll get ghosting like this. But what really kills the time series is that this ghosting will be non-reproducible because you capture the heart, it's beating at different, each line will capture the heartbeat at a different phase and a breathing at a different phase. And so these lines will be reshuffled, not really reshuffled, but the distance between the phase will be different depending on how you capture the physiology. So your ghosting will be different over time. So that means, that's why multi-shot techniques are incredibly unstable relative to bold contrast for time series imaging. That's why nobody does it. So almost nobody does it, unless you have really good navigators which actually realign the lines. Okay, so this is an approximate timeline of the evolution of echoplanar imaging. You know, back when Mansfield conceived of it, before the hardware was available to do it, all the way to in '96, it became somewhat standard on clinical scanners. Luckily, there was enough clinical applications to sort of drive the development of echoplanar on clinical scanners. By 2000, you had more high performance gradients. 2002, parallel imaging for high resolution EPI came about. About 2006, 1.5 millimeter cubed EPI was possible. And at 2009, single shot sub-millimeter EPI was possible. So I should actually update this for talking about multiband techniques as well. So we can do higher resolution at much shorter TRs now, and that seems like the next thing that the field will embrace as it becomes available on clinical scanners. So all of this is actually interesting, is that it is driven, unfortunately or fortunately, by the fact that echoplanar imaging has other uses for perfusion imaging and things like that. So they are on clinical scanners. If this all had to be sort of home-built stuff that we had to sort of develop, the evolution of functional MRI would have been relatively a lot slower. But likewise, though, it's also held back a little bit by industry. So for instance, the technique that I mentioned Alan Koretsky first developed, arterial spin labeling. Great technique. It could have been extremely useful clinically. Unfortunately, or it could have been extremely useful for fMRI, but unfortunately it was not quite as useful clinically. And so none of the vendors actually decided to buy the license to it. So it was patented and never used for 17 years until never used clinically on clinical scanners, so never disseminated to a lot of people for about 17 years until the patent ran out. And so finally, recently now, Siemens and GE have perfusion sequences because now they didn't have to buy the patent, and so it's very easy to implement. So, okay, that's just so it can go both ways. Industry can sometimes hold things up. Industry can accelerate things. I'm not going to go too much into that other than saying that we no longer need local grading coils for echoplanar imaging. We still could use local grading coils for doing high performance diffusion imaging, but I'm not going to get into that right now. Right now we have much more beefed up gradient amplifiers, and that allows us to do extremely high speed imaging with whole bore echoplanar imaging scanners. In fact, right now, our main limitation is not necessarily the hardware, it's more the biologic limit. So if you switch your gradients too fast, then you start getting peripheral nerve stimulation. So that we're up against those biologic limits as opposed to hardware right now. Okay, so finally, the last factor I want to mention is the prevalence of MRI scanners. And like I mentioned, this is where industry, the rest of MRI, the clinical application of MRI really helped fMRI. Because suddenly, every scanner that was used clinically was potentially a brain imaging scanner. You didn't have to make a separate scanner. So this is pretty much the trajectory of a number of papers published per year up until 96. And to me, it looks like the slope of the curve changed radically, or changed a lot. It would have been sort of maybe like that. But 96, when the first EPI was sold on clinical scanners, it became a little bit steeper, since more people had the ability to do functional MRI right away because they had a clinical scanner they had access to. Okay, and so the last part of this, I just want to mention that, so this is a nice slide that shows, in basically 91 to 94, we were just sort of using fMRI as a proof of concept. We were tapping fingers, shining light in people's eyes, and it wasn't really proven. So now, by 2001, and now even more so, it's used for almost everything, as far as everything from, looking at emotion. We have a whole program here in NIMH that looks at emotion. Half the people, or most of the people who do that sort of research, emotional disorders, use imaging, cognition, all kinds of things. So it's much more, it's become completely disseminated as far as that's concerned. And another way I like to look at this is that the field has been evolving along four sort of pillars, and they all interact. The technology drives things as far as we're continuing to get better coil arrays, we're continuing to go to higher field strength, higher resolution, novel pulse sequences that pull out unique types of contrast. We're continuing to develop based on what we can look at here, based on the stability of what we can see. We're developing better, more sophisticated methodology, such as multivariate analysis, machine learning approaches, multimodal integration, real-time feedback, things like that. And of course, we're still trying to understand the signal as well. So as we better interpret the signal, so we're still trying to understand what the neural sources of resting state fluctuations are, what types of dynamics are really physiologically interesting in the signal, and what is the upper functional resolution. We're still trying to figure this out. So as we do, it feeds into the methodology, helps to maybe even motivate the technology, and finally feeds into applications. So I think, with that, I'd like to end my first talk. So this is just for a quick summary of some of the landmark developments. You can't even see this. I can barely see it. At least if you want to download the slides, it's a reference to some of the papers that sort of like push the field along. The first sort of visual, sort of continuous visual, event-related fMRI, pushing the temporal resolution, things like that. So, okay. All right. Thank you. Thank you. So maybe I'll pause just for a second for any questions. Yes.
ASL sequences you mentioned currently available at NIH?
Yes. Yeah. There's a few that are, they've always been somewhat available at the NIH, because luckily we have enough people here developing ASL. So they've been sort of rough sequences that existed, but now they're, I think, we're in the process of getting, we're thinking of getting one of the, at least ASL on the GE scanners. I think we have ASL on the Siemens, right? Or, Sean?
We don't have the Picasso.
Right, we don't have the Picasso on the Siemens, but Anyway, but there's some version that either we're getting or we're planning on getting. So, And like I said, though, we have other sequences that can do ASL. It's just the added processing that you have to do. It's harder for the user to sort of take that data and work with it. But if you want to collaborate with one of the physicists here or whatever, they can do that. So, okay.